Picture this, a cosmic monster so powerful that not even light can escape its gravitational grip. It's the ultimate devourer of the universe, a place where the laws of physics as we know them seem to break down. But what if I told you this monster isn't as black as it appears? Today, we're diving into one of the most fascinating phenomena in the cosmos, Hawking radiation, the process that reveals how black holes can actually shine. You're about to discover how quantum mechanics completely flips our classical understanding of black holes. These cosmic giants, once thought to be eternal prisons for light, are now revealed to be subtle emitters of energy. It's a journey that takes us from the edge of a black hole's event horizon to the very frontier of modern physics. But before we unravel this cosmic mystery, make sure to hit that like button and subscribe to Exploring the Universe so you don't miss out on more mind-blowing content about the wonders of astronomy. Trust me, you won't want to miss what's coming next. Let's start with the basics. What exactly is a black hole? Imagine a region in space where gravity is so intense that nothing, not even light, can escape its pull. It's like a cosmic vacuum cleaner, but on a scale so massive, it's hard to wrap your head around. The story of black holes begins with Albert Einstein's theory of general relativity, which he published over a century ago. Einstein's equations predicted the existence of these bizarre objects, but even he was skeptical at first. It wasn't until decades later that scientists like Carl Schwarzschild and John Wheeler began to take the idea seriously. And then, in 2019, humanity achieved something truly extraordinary. We captured the first ever image of a black hole. That iconic photo of the supermassive black hole at the center of the galaxy Messier 87 was a monumental moment in science, proving that these cosmic monsters are very real. Here's a fun fact to blow your mind. The smallest known black hole has a mass just 3.8 times that of our Sun, but on the other end of the spectrum, supermassive black holes can weigh in at billions of times the Sun's mass. These giants lurk at the centers of galaxies, shaping the very fabric of the cosmos. So black holes are more than just dark, mysterious voids. They're cosmic architects, shaping the universe in ways we're only beginning to understand. And this is just the start of the story. Stick around, because things are about to get even more fascinating. Now let's talk about one of the most fascinating features of a black hole, the event horizon. Picture yourself standing at the edge of Niagara Falls. You see the mighty river flowing, getting faster and faster as it approaches the edge. There's a critical point where the water moves so rapidly that even if you were the strongest swimmer in the world, you couldn't swim against the current. That's exactly what the event horizon is like in a black hole. The event horizon is nature's ultimate point of no return. It's not a physical surface you can touch or see, it's more like an invisible boundary in space. Once anything crosses this boundary, whether it's light, matter, or even information itself, it's on a one-way trip into the black hole's depths. Here's something mind-blowing. If you were watching your friend fall into a black hole as they approached the event horizon, they would appear to slow down and freeze in time, growing fainter and redder until they eventually fade away. But from their perspective, they would fall right through, experiencing nothing unusual at the boundary itself. This strange effect happens because time itself behaves differently near a black hole. The size of an event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be just about 3 kilometers in radius. But for the supermassive black hole at the center of our Milky Way galaxy, called Sagittarius A star, the event horizon is about 12 million kilometers across. That's about 17 times the size of our Sun. The term event horizon was first coined by Wolfgang Rindler in 1956, but the concept itself emerged from Carl Schwarzschild's work during World War I. While serving in the German army, Schwarzschild solved Einstein's field equations and discovered this peculiar boundary where escape becomes impossible. Think about this. If Earth were somehow compressed to become a black hole, its event horizon would be smaller than a penny, about 9 millimeters across. Yet it would still have the same mass and gravitational pull as our entire planet. And here's a question that has puzzled scientists for decades. What happens to the information about objects that cross the event horizon? Does it get destroyed, or is it somehow preserved? This is known as the information paradox, and it's one of the biggest mysteries in modern physics. So what do you think happens to an object once it crosses this cosmic point of no return? What secrets lie beyond the event horizon? Share your theories in the comments below. Maybe you'll come up with an idea that even scientists haven't thought of yet. Remember, sometimes the most significant breakthroughs in science come from asking seemingly simple questions. Your curiosity about what lies beyond the event horizon puts you in the company of some of history's greatest minds, from Einstein to Hawking, who've pondered these same cosmic mysteries. Now, this is where things get really wild. Just when you thought black holes couldn't get any stranger, quantum mechanics steps onto the stage and completely changes the game. You see, the empty space around us isn't really empty at all. It's actually buzzing with activity at the quantum level. In the seemingly empty vacuum of space, pairs of particles constantly pop into existence and then immediately destroy each other. These are called virtual particles, and they're like cosmic dancers performing an endless waltz of creation and annihilation. It happens so fast that we usually can't detect it, but it's happening all around us all the time. Imagine shaking a blanket and seeing tiny dust particles appear and disappear in the sunlight. It's kind of like that, but on an unimaginably smaller scale. But here's where it gets fascinating. When these particle pairs appear near a black hole's event horizon, something extraordinary happens. Picture a couple dancing on the edge of a cliff. Suddenly, one dancer falls off while the other spins away to safety. That's basically what happens near a black hole. One particle falls in while its partner escapes into space. This escaped particle becomes real, taking energy with it from the black hole. This phenomenon was first proposed by Stephen Hawking in 1974, and it completely revolutionized our understanding of black holes. Imagine the scene. A young physicist in his early 30s, already dealing with a devastating diagnosis of ALS, sitting in his office at Cambridge University when this incredible insight struck him. He realized that black holes weren't eternal after all. They could actually lose mass and eventually evaporate. The story goes that when Hawking first made this discovery, he was so excited that he couldn't sleep for several days. He knew he had stumbled upon something revolutionary. At first, many scientists were skeptical. How could anything escape from a black hole? But Hawking's mathematics was solid, and his prediction has become one of the most important theoretical discoveries in modern physics. Here's something mind-bending to think about. The particles that escape aren't actually coming from inside the black hole. They're created from the vacuum just outside the event horizon. It's as if the black hole is surrounded by a quantum fog of particles, and occasionally, some of these particles manage to break free and escape into space. The temperatures involved in this process are incredibly extreme. A black hole the mass of our sun would have a temperature of only about 1/10 millionth of a degree above absolute zero. That's colder than the cosmic microwave background radiation that fills our universe, but smaller black holes would be much hotter, and they would evaporate much faster. Hawking's work on this phenomenon earned him worldwide recognition and helped bridge the gap between quantum mechanics and gravity, two fundamental theories that had seemed impossible to reconcile. It showed us that even the most absolute rules of classical physics could be broken when quantum effects come into play. The discovery of this radiation, now known as Hawking radiation, raises even more intriguing questions. What happens to all the information that falls into a black hole? Does it eventually come out in the radiation? These questions continue to puzzle physicists today, leading to what we call the information paradox. But that's a story for another time. Remember, every time you look up at the night sky, these quantum dances are happening all around us, invisible to our eyes, but fundamental to the way our universe works. It's a reminder that reality is far stranger and more wonderful than we could ever imagine. Let's dive deeper into one of the most mind-bending phenomena in the universe: Hawking radiation. Remember those particle pairs we talked about? When one particle escapes from the black hole's event horizon, it doesn't just wave goodbye and float away. It actually steals energy from the black hole. This is where things get really interesting. Every time a particle escapes, it carries away a tiny amount of energy. And according to Einstein's famous equation, E equals mc squared, energy and mass are two sides of the same coin. This means that each escaping particle is essentially taking a microscopic piece of the black hole with it. It's like watching an enormous ice cube slowly melt away in the summer sun, except this process happens over an unimaginably longer timescale. Now here's something that would have shocked scientists a century ago. Black holes aren't forever. They're slowly evaporating, losing mass bit by tiny bit through this radiation process. It's as if these cosmic giants have a very, very slow leak. The smaller the black hole, the faster it evaporates, kind of like how a small ice cube melts faster than a large one. Want to hear something that will blow your mind? A black hole with the mass of our sun would take a mind-boggling 10 to the power of 67 years to evaporate completely. To put that in perspective, our universe is only about 14 billion years old. We're talking about a number so large that if you tried to write it out, you'd need 67 zeros after the 1. By that time, the universe as we know it might be unrecognizable. But here's where it gets even more fascinating. While stellar mass black holes take an eternity to evaporate, tiny black holes, if they exist, would evaporate much more quickly. A black hole the size of a mountain would vanish in less than a second, releasing an enormous burst of energy in its final moments. Scientists are actually searching for these miniature explosions in space, hoping to catch a glimpse of a black hole's final farewell. The discovery of this evaporation process completely changed our understanding of black holes. Before Hawking's work, we thought of black holes as cosmic vacuum cleaners that could only grow larger and larger, eventually consuming everything in their path. Now we know they're more like cosmic leakers, slowly returning their stolen mass back to the universe. This also leads to an interesting prediction about the far, far future of our universe. Eventually, after an almost incomprehensible amount of time, all black holes will evaporate completely. Even the supermassive monsters at the centers of galaxies will ultimately disappear in a final burst of radiation. Here's a fun fact that few people know. The larger a black hole is, the colder it gets. A supermassive black hole, like the one at the center of our galaxy, is actually colder than the space around it. It's so cold that it's almost at absolute zero, the lowest possible temperature in the universe. This makes detecting Hawking radiation from these giant black holes practically impossible with our current technology. The story of Hawking radiation reminds us that in science, nothing is truly absolute. Even the darkest, most mysterious objects in the universe aren't immune to the strange rules of quantum mechanics. It's a testament to human ingenuity and imagination that we can understand these incredible processes happening billions of light years away. Think about it. Every black hole in the universe is slowly disappearing, counting down to its final moments. It's like a cosmic countdown clock running in super slow motion. While we'll never be around to see the end of this process, just knowing it's happening adds another layer of wonder to our already magnificent universe. Now we're reaching one of the most puzzling mysteries in modern physics, a puzzle so profound it kept Stephen Hawking awake at night and continues to baffle scientists today. Let's talk about the information paradox, a problem that sits right at the intersection of quantum mechanics, gravity, and the nature of information itself. Here's the big question: what happens to information when it falls into a black hole? And by information we mean everything that makes something what it is. Its quantum state, its structure, every single detail about it. According to quantum mechanics, information can never be truly destroyed. It's like nature's version of the old saying, nothing is ever really lost. But black holes seem to break this rule. When something falls in, it appears to be gone forever, reduced to nothing but mass and energy. Or is it? When Hawking discovered that black holes evaporate, this puzzle became even more perplexing. If black holes eventually disappear, what happens to all the information they've collected over their lifetime? This question has led scientists down some fascinating paths, including string theory and quantum gravity. String theory suggests that our universe might have more dimensions than we can see, and information might be preserved in these hidden dimensions. Imagine your favorite book falling into a black hole. String theory hints that the information about every word, every page, might be encoded on the black hole's surface, like a cosmic library card catalog. Quantum gravity, on the other hand, tries to combine Einstein's theory of gravity with quantum mechanics. Some scientists believe this might reveal how information could leak out of black holes, encoded in subtle patterns within Hawking radiation. It's like trying to reconstruct a shredded document. The information is there, but it's scrambled in ways we don't yet understand. In 2016, Stephen Hawking, along with Malcolm Perry and Andrew Strominger, proposed that information might be stored in something called soft hair, quantum states on the surface of the black hole's event horizon. This idea suggests that black holes might have a sort of memory, keeping track of everything that falls into them. Here's a mind-bending thought. What if the information isn't actually lost, but just transformed into a form we can't yet recognize? Imagine throwing a book into a fire. The words seem to be destroyed, but in theory, if you could track every atom and particle from the smoke and ashes, you could reconstruct the book. Could something similar be happening with black holes? This debate has sparked some of the most heated discussions in theoretical physics. Leonard Susskind and Gerard de Hooft proposed the holographic principle, suggesting that all the information about three-dimensional objects might be stored on a two-dimensional surface, like the event horizon of a black hole. It's similar to how a credit card hologram can store a three-dimensional image on a flat surface. So here's where I want to hear from you. What do you think happens to information in a black hole? Is it lost forever? Or is there some clever way nature preserves it? Share your theories in the comments below. Who knows? Maybe you'll propose something that helps solve this cosmic riddle. And while you're pondering these deep questions about the nature of information and black holes, here's another thought to consider. If you could observe a black hole up close, what would you most want to discover? Would you try to solve the information paradox, or would you look for something else entirely? Drop your astronomical aspirations in the comments. Don't forget to support our exploration of these cosmic mysteries by hitting that like button and subscribing to Exploring the Universe. Each like and subscription helps us continue bringing these fascinating topics to curious minds like yours. Remember, some of the greatest scientific discoveries started with simple questions, just like the ones we're asking today. Now, let's dive into some absolutely mind-blowing facts about black holes that will change the way you think about these cosmic giants. First up, let me tell you something spectacular. Supermassive black holes are nature's most powerful particle accelerators. These cosmic monsters can shoot out enormous jets of particles at speeds approaching the speed of light. These jets, called relativistic jets, can stretch for thousands of light years. That's far enough to reach multiple galaxies. Imagine a fountain of energy so powerful it could cross the distance between our Milky Way and our neighboring galaxies. These jets are like cosmic lighthouses, beaming across the universe and helping astronomers spot black holes from incredible distances. Here's some breaking news from the scientific world. In 2023, scientists made a breakthrough that would have made Stephen Hawking jump with joy. Using specially designed laboratories on Earth, researchers created something called analog black holes, systems that behave like black holes without actually being black holes. Think of it as a simulation, like testing how a boat behaves in a wave pool instead of the ocean. Using these analog systems, they detected patterns that look remarkably similar to what Hawking predicted would happen around real black holes. This is the closest we've ever come to observing Hawking radiation in action. Now, let's bust a major myth that's been floating around for years. Black holes don't act like cosmic vacuum cleaners, sucking up everything in sight. If we replaced our sun with a black hole of the same mass right now, Earth wouldn't get sucked in. We'd just continue orbiting as usual, though we'd definitely freeze without the sun's warmth. Black holes only affect objects that come very close to them within their gravitational influence. It's like having a very deep well in your backyard. It's only dangerous if you get too close to the edge. Speaking of fascinating facts, did you know that some black holes are actually messy eaters? When they feed on gas and dust from nearby stars, they can become so bright they outshine entire galaxies. These are called quasars, and they're some of the brightest objects in our universe. It's like watching a cosmic light show powered by nature's most extreme objects. Here's another mind-bending fact. Time behaves very strangely near black holes. If you were watching someone fall into a black hole, they would appear to slow down and freeze in time as they approach the event horizon, while from their perspective, everything would seem normal. This effect, called time dilation, was predicted by Einstein's theory of relativity and shows just how weird space and time become in extreme conditions. And here's something that might surprise you. We're actually pretty safe from black holes here on Earth. The nearest known black hole is thousands of light years away, and it's not heading in our direction. Space is so vast that the chances of a black hole wandering close enough to affect our solar system are incredibly small. You have a better chance of winning the lottery multiple times in a row. One of the most recent discoveries about black holes came from the Event Horizon Telescope team, who captured the first ever image of a black hole's shadow in 2019. This remarkable achievement required telescopes across the entire planet working together as one giant Earth-sized observatory. It's like taking a picture of an orange on the moon from Earth. That's how precise their measurements had to be. These discoveries keep reminding us that the universe is far more fascinating than we could have imagined. Every time we think we understand black holes, they surprise us with something new. They're like cosmic gift boxes that keep revealing new secrets every time we look at them more closely. Remember, our understanding of black holes is still evolving. What we know today might be just the tip of the cosmic iceberg. Who knows what other incredible discoveries await us as we continue to study these mysterious objects? Maybe you'll be the one to make the next breakthrough in black hole physics. Now, we've arrived at the most mind-blowing revelation of our journey through black holes and Hawking radiation. Are you ready for something that will completely transform how you see the universe? If Hawking radiation proves to be correct, and mounting evidence suggests it is, we might be standing on the threshold of the greatest breakthrough in modern physics. You see, for nearly a century, scientists have been trying to solve what seems like an impossible puzzle: how to reconcile Einstein's theory of general relativity, which explains gravity and the large-scale structure of the universe, with quantum mechanics, which governs the behavior of the smallest particles. These two fundamental theories, both incredibly successful in their own domains, seem to speak completely different languages. It's like having two brilliant translators who can each speak to half the world, but can't talk to each other. But here's where it gets exciting. Black holes, through Hawking radiation, might be the key to making these translators finally understand each other. Think about it. In a black hole, we have gravity so intense it warps the fabric of space-time itself. That's pure Einstein territory. But then, We have quantum effects creating radiation at the event horizon. That's quantum mechanics in action. Black holes are the only places in the universe where these two forces meet in such an extreme way. They're like cosmic laboratories where nature itself is trying to tell us something profound about how the universe really works. But there's more, and this is where things get really interesting. Hawking radiation might help us understand not just how the universe works, but where it's all heading. As black holes slowly evaporate through this radiation, they're giving us clues about the ultimate fate of everything in existence. Imagine holding a book that tells you not just how the universe began, but how it might end. That's what we're dealing with here. Let me share something fascinating that most people don't know. When Stephen Hawking first proposed this radiation mechanism, he wasn't actually looking for it. He was trying to prove that black holes could never get smaller. Instead, he found exactly the opposite. It's one of those beautiful moments in science where nature surprises us with something even more amazing than what we were looking for. And here's another thought that will blow your mind. If we're right about Hawking radiation, every black hole in the universe is slowly connecting these two fundamental theories, performing an experiment that we could never hope to replicate in any laboratory on Earth. They're like cosmic computers, processing information in ways we're just beginning to understand. The implications are staggering. We might be on the verge of discovering what physicists call the theory of everything, a single explanation that could unite all the forces of nature. And to think the key to this profound mystery might have been hiding in what we once thought were the darkest, most impenetrable objects in the universe. Isn't it incredible how the universe works? Sometimes the answers to our biggest questions come from the most unexpected places. Black holes, once thought to be cosmic dead ends where physics breaks down, might actually be the very things that help us unlock the deepest secrets of existence itself. As we reach the end of our cosmic journey today, let's take a moment to reflect on the incredible revelations we've uncovered about black holes and Hawking radiation. We've ventured far beyond the traditional view of black holes as cosmic vacuum cleaners, discovering instead a universe that's even more fascinating than we imagined. Remember how we started this journey thinking of black holes as purely dark entities? Well, now we know better. These cosmic giants actually shine with their own unique radiation, telling us stories about the fundamental nature of our universe. It's like discovering that the darkest cave you've ever seen actually contains its own source of light, completely changing how we see everything around it. Stephen Hawking's brilliant insight about this radiation didn't just change our understanding of black holes, it opened up an entirely new way of looking at the cosmos. It's amazing to think that this discovery came from someone who, despite facing enormous physical challenges, never stopped exploring the mysteries of the universe with his mind. His work created a bridge between two seemingly incompatible theories, quantum mechanics and classical physics, showing us that the universe might be more unified than we ever imagined. But perhaps the most exciting part of all this is that we're still at the beginning of our understanding. Every answer we've found has led to new questions, each more fascinating than the last. The implications of Hawking radiation reach far beyond black holes, touching on everything from the birth of the universe to its ultimate fate. You know what's really incredible? We're living in an age where these cosmic mysteries are being unraveled right before our eyes. The same principles that Hawking worked out with pen and paper are now being tested with some of the most advanced technology humanity has ever created. We're literally watching science fiction become science fact. This journey we've taken together today is just the beginning. There's so much more to explore, so many more mysteries to uncover. I hope this discussion has sparked your curiosity about the cosmos as much as it continues to fascinate me. The universe is out there, full of wonders waiting to be discovered, and together we can explore its deepest secrets. If you've enjoyed this cosmic adventure and want to join me for more mind-bending explorations of the universe, make sure to subscribe to Exploring the Universe. Hit that notification bell so you don't miss any future discoveries and mysteries we'll explore together. Give this video a like if you've learned something new today, and share it with your friends who might also be fascinated by these cosmic wonders. Remember, every time you look up at the night sky, you're looking at a universe that's far more mysterious and amazing than we ever imagined. And who knows, maybe the next great discovery about black holes or quantum physics will come from someone watching this video right now. Join me next time as we continue our journey through the cosmos, uncovering more of its incredible secrets. Until then, keep looking up and keep wondering about the mysteries that surround us. Follow me on social media for daily doses of cosmic curiosities and behind-the-scenes looks at the universe we call home. Thank you for being part of this amazing journey through space and time.